Okay, do you see it now?
Yes.
Yes.
Okay.
Let me know.
Okay. Yeah, you can start, Alejandra.
Okay. So good afternoon, everyone. Welcome to another seminar of a series. Today we have the pleasure of hearing from Irina Dvorkin. I hope I pronounced that okay. Irina got her PhD degree in 2014 at the Tel Aviv University. She was a research assistant in that university and was also postdoc fellow at the Max Planck Institute for Gravitational Physics and the Institut d'Astrophysique de Paris. Currently, she is a lecturer at the Sorbonne Université, and her research interest includes evolution of galaxies, modeling of the evolution of galaxies, with special focus on the chemical composition of the galactic gas and the birth rates of massive stars, neutron stars, and black holes. Today, she's going to tell us about the origin of gold and other heavy elements. So Irina, whenever you're ready, you may start.
Okay, thank you very much. Thank you, Marina and Alejandra, for this invitation. It's a pleasure to give this talk, even by remote. So today I'm going to tell you about the origin of some of the heavy elements in the universe. So from this in this plot on the right, what we see is the composition of, well, the abundances of different chemical elements in the solar system. So apart from some light elements that are formed during Big Bang nucleosynthesis, a lot of the elements that we know are in this green category. They're formed during stellar evolution. So this is how actually stars get the energy by producing heavier and heavier elements up until the iron peak. However, elements above the iron peak cannot be formed through this way because the binding energy per nucleon starts to decline. And so we need other processes to form these heavier elements. This can be done by neutron capture. So you have a nucleus and you capture more and more neutrons into the nucleus. And this can be done in two types of processes: the slow process, or S process, or rapid process, or the R process. Now, slow and rapid is relative to the beta decay rate. So if it's much slower than the beta decay, then you gradually capture neutrons and then beta decay back to the value of stability and build up your nucleus like this. And this actually happens during the asymptotic giant branch phase of the stellar lifetime. And now there is also another type of process which is rapid relative to beta decay, so that the nucleus captures many neutrons very rapidly and travels very far away from the value of stability. It finds itself in a radioactive zone, so it decays then quickly through beta decay, in fact, back to the value of stability. And this is a very efficient way to form very heavy nuclei. And actually it's half-half, so about half of the heavy elements are formed by the S process and another half by the R process. And in particular, we're going to be interested in elements that are formed exclusively or almost exclusively by this R process, because the site where this happens is not yet completely clear, as I'll show you in the next few slides. So this is a very specific, very interesting process, because to be very efficient in rapidly capturing a lot of neutrons, you need huge temperatures and huge densities and very neutron-rich matter. So there are some elements like gold, which is admittedly somehow an eye-catching title for this talk. In fact, most of the talk is not going to be about gold, but nevertheless, gold is an R-process element, and also other elements like europium, platinum, and uranium, and some of them are unstable. And so the question is, how do these elements, so you see here the R process, first R process peak and second R process peak, how do these elements actually form? So where do we observe these elements? So, well, as I said, most of my talk is not going to be about gold, unfortunately, but it's going to be about another R process element, europium, for the simple reason that europium is easier to observe in stellar spectra. So in fact, it's found in the spectra of a lot of stars, for example, in the Milky Way. So here I show you a plot of stars in the Milky Way, halo and disk from the Saga database. And in this plot, okay, I'm sure you'll know, but so we are all on the same base. So this plot shows the abundance of iron on the x-axis and europium relative to iron on the y-axis, and it's in solar units and logs. So that means that 0, 0 is exactly solar abundance, -1 is 1/10 of solar, -2, 1/100th of solar, etc. So we see here the abundances of europium with its out-process element relative to iron for a bunch of stars. And what we see here is actually there are two characteristics of this plot. One is that we have some very low metallicity stars here, -3, so that 1,000th of the solar value, that are nevertheless very, very rich in europium. So they're overabundant in europium relative to the sun. I remind you that actually the axis of iron abundance is somehow proportional to the time, actually, that time of the evolution of the galaxy, because of course iron is released, is synthesized in supernovae, and so the more stars we build, the more stars explode as supernovae, and then the more iron we have in the interstellar medium from which these stars, actually the next generation of stars, are created. So these stars that have very low iron abundances have formed very early on in the evolution of the Milky Way, and nevertheless they are very much enriched in europium. So the question is, how is this possible? Another question we can ask is why there is such a large scatter in this plane, especially at low metallicities. So it means that stars that formed roughly at the same epoch could have very different abundances of europium. So that already tells us that europium is produced in a different process than iron. So that means in different process than supernovae. So in this this low metallicities, the iron is produced by the core collapse supernovae. And one of the early assumptions was that europium or out-process elements are produced also in supernova explosions, but actually it cannot be the case because then they will be tightly correlated, which is not what we see here. Another site related where we find the out-process elements are dwarf galaxies. For example, here I show you the results or measurements from the Reticulum 2 dwarf galaxy. That's a famous galaxy for people who study out-process elements, because what was observed there are, again, very high abundances of europium, this time relative to just hydrogen, for very metal-poor stars. So again, stars that were formed early on, and it was hypothesized in this paper that in fact they think there is just one event that produced all of this europium and then enriched the ISM from which the stars formed. Now you can also see here for 4 of the stars in this galaxy the abundance patterns for a few heavy elements. And now in purple they show the relative abundances for out-process elements, and in yellow for S-process elements. And what they show in this plot is that indeed the relative abundances of different elements that they could measure in the stars are actually they are consistent with being produced in an R process and not an S process. So this is where we should look. So now, where could these R process elements be produced? So one good candidate are actually binary neutron star mergers, or black hole neutron star binaries that merge. So I'm sorry, it's a bit of, there are a bunch of stuff on this slide, but as you'll know, we now have one magnificent event where we captured a merger of 2 neutron stars, and we observed it in gravitational waves. So we are certain these are 2 neutron stars, and we observed it also across the entire electromagnetic spectrum. So in particular in infrared and in optical. And why is that important? Because it proved that indeed the merger of these 2 neutron stars produced produced our process elements. Now, how does that go? So this is a sketch here that that shows this process. So you have, well, it doesn't show it from the beginning, but imagine you have two neutron stars that merge. They produce some merger remnant, whatever. But what is important for us here is that there is matter that is ejected from the merger. And this matter is obviously extremely neutron rich because these were two neutron stars. Now, in this ejected matter, these R process elements are produced because the temperatures and the densities are just trying to produce these R process elements. But as I told you, they are produced very far from the value of stability, so they quickly decay back and emit energy. So this radioactive decay actually powers then the emission or thermal emission from this ejecta. So it's kind of similar to what happens in the supernova, only different time scales and different types of elements that are produced. And so we expect a particular light curve from this event. And this is exactly what we see here. So this is again, this is a model for light curves across different spectra, and as a function of time after the merger. So you would expect that of course, the light curve decreases and becomes redder and redder as the ejecta expands. From this light curve, we can actually measure the amount of energy that was produced, and then the amount of actual R process elements that were produced by this event. And indeed, it was about 5% of the solar mass of R process elements, which then means it produced about a few Earth masses in gold just in this one merger of two neutron stars. So we know that binary neutron star mergers are very rare events, about 1% of the core collapse supernova rate. So that also kind of answers our what we thought before. So that should all be good. The one problem is that we expect there will be very large time delays between the formation of progenitor massive stars and the merger of two neutron stars. So we expect that the neutron stars will be formed with very large separation, and it would take them up to giga years to merge. Whereas we saw earlier that there are stars that have low metallicities, that means that they formed very early on in the galaxy, yet had high enrichment rates in our process elements. So this is one point to look at. Okay, so this is again at the same point. So this again shows I forgot to say, this phenomenon is called a kilonova, and this again shows the kilonova that was observed in August 2017 as the electromagnetic counterpart of the gravitational wave event of the binary neutron star merger. So this kilonova again is a transient powered by the radioactive decay of our process elements. Here you see on the right the measurements in red, and several models that were fitted in this particular paper. There were a bunch of papers, well, of course, a huge amount of papers, but several discoveries papers, which fit these kilonova models, and that we could deduce the amount of matter ejected in this event. Now, the identification of the exact elements produced is still very challenging. Now, here on this small plots in the middle, you see sort of attempts to identify cesium and tellurium, I guess, lines in the spectrum of this event. It's still not maybe extremely convincing that these are the elements these are the absorption lines on these elements. So we still need to actually identify the elements in the spectra of future kilonova, hopefully. But this is not the only candidate site to produce our process elements. You can also, the other hypothesis is that you can produce them in core collapse of massive stars. Now, I told you that if you produce it in regular core collapse, it doesn't really explain the observations, first because they are too frequent, and second because the relative abundances of our process elements that are produced in regular supernovae cannot explain the relative abundances in the Milky Way, but in special types of core collapse supernovae where they have very fast rotation and very high magnetic fields, and these types of events are also very rare, you can, there were some models that predict you can produce even up to 1 solar mass of our process elements per event for these types of collapsed stars. So this is the schematic that is shown on the right here. If you have a massive star that collapses to a black hole, this ejecta, under the reception of very high magnetic fields, you can also form some R process elements. That this was not actually never observed directly, and there are some theoretical difficulties in producing these events. So which one is correct? Maybe both at the same time. In fact, we know how much our process elements there are in the galaxy because, well, through the plots that I showed you at the beginning, so we can count how much mass we have. And so we can have either events that are very rare here on the events that are rare. So this shown the event rate per mega year in the galaxy, in the Milky Way. But each event produces a lot of our process elements, or events that are very frequent, but each one produces just a little bit of their process elements. And to explain the mass in the galaxy, you need this to be along this green line. And in fact, a lot of evidence points to the binary neutron-star mergers being the dominant site. For example, you can, from this gravitational wave event, 1709-17, where we measured both the rate and the mass, well, roughly, it kind of sits with what we expect here along the green line. It also is consistent with the rate of short GRBs. Now, short GRBs are also produced in the binary neutron-star mergers. Now, we also know that thanks to this event, this same gravitational wave event. And there are also some kilonova, macronova is the same thing, some kilonova candidates where we could measure the mass produced in this candidate. And it kind of also all convergence towards this part of this plot. So it seems that binary neutron stars can indeed explain the abundances of our process elements. So if you count how many neutron star mergers there are in the universe based on this one event, granted, and how much mass of our process elements is produced per event, you kind of can explain the mass that we see today. However, oh, sorry, it's stuck. Okay. However, when you do a detailed galaxy evolution model, it turns out that it's not as simple as it seems. Because of the thing that I told you in the beginning is that binary neutron-star mergers take a lot of time to merge. They're formed with huge separations, and then it's difficult to explain early enrichment. So here I show you two types of models, but there are many more studies on this. So in the upper plot, I show you a plot from Cote et al., which is a semi-analytic plot. It's the same plane as I showed you for the Milky Way measurements, and here the crosses are the measurements, and the lines are a model where here they assumed a constant time delay between the formation of the progenitor star and the merger of the binary neutron stars. So you see that they can somehow explain the observations only if this delay time is 10 mega years. So that means that you form the massive stars. Well, of course, relatively quickly they collapse, let's say, and form a binary. But then it takes only 10 mega years for the binary to merge. But that's extremely short. Most of them probably don't merge at this time scale, and this is what we know from stellar evolution models. And when they take the delay of even slightly larger of 30 mega years, already they cannot at all catch this evolution here. Now, on the bottom plots, I show you the models from Van der Voort, which are numerical models, slightly more detailed ones. And here on the left, again, the sort of points are observations. And the model in this paper are the gray and black lines. And here on the left, we just neutron star mergers. You see that also they have difficulty explaining this early enrichment of stars in the galaxy. Whereas if they assume that actually the enrichment is mostly by this rare Hall collapse supernovae, which is unspecified the exact mechanism in this paper, it kind of works slightly better. But nevertheless, this shows kind of some kind of difficulty to explain this its own enrichment by just binary neutron stars. So what do we need to know in order to actually go from these very nice light curves, which explain how our process elements are produced in a binary star merger, to explain the abundances of stars that we observe in the galaxy? So first of all, we need to know the BNS merger rates, the merger rates, of course, and the relation to host galaxy properties, because the Milky Way obviously evolves through the ages. We need to know knowing, let's say, the star formation history of the Milky Way, we still need to know the efficiency of forming binaries, and this is deeply related to stellar evolution models and the tidal distribution between formation and merger. Of course, we need to know the yields of our process elements, so how much mass we produce per event. We also need to know how much of these our process elements or metals are retained in the galaxy, because you can, and I will just come back to in the next slides. You can imagine that if you have an energetic event like a merger of or a core collapse supernovae, it ejects these star process elements in the ISM, but a lot of them will leave the galaxy, especially if it's a dwarf galaxy. So what is interesting about the measurements that I showed you before of the dwarf galaxy, Reticulum 2, is that it was able to retain, obviously, a lot. Well, it's what we see, to retain a lot of these star process elements inside, even though the event they produced them was probably very energetic. Then we need to know the mixing timescales of metals in the galaxy to explain probably also this dispersion, and take into account probably the fact that if it's binary stars, they have some birth kicks, so they may have actually merged at a different place than their progenitor stars were born, where the ambient iron abundance is actually different. Okay. No. Okay. So just some words on the formation and merger rates of binary neutron stars. This is just to to make an impression that this is an extremely complex process. I want to go through this diagram, but basically you start with two massive stars. They go through a bunch of events in their lifetime of the binary, and in fact, it depends on a lot of effects that are not very well understood to this day. For example, one of the crucial events is a common envelope phase, where you have when one of the massive star already formed for a neutron star, while the other has not, and then the neutron star is engulfed in the envelope of the star that is still there, and they co-evolve the core of the massive star and the neutron star in such a way as to, so they interact also with the envelope. This is why it's called common envelope. And if the interaction is efficient, the envelope is ejected, and then when the second neutron star formed, it's relatively close to the first neutron star, so that they can quickly merge. If the interaction is not efficient, then they're still far away when they form a binary, and then they cannot merge during the age of the universe. And in this plot, what I show you is from Santoliquio et al. The rate of binary star mergers is a function of redshift, and this rate depends on this efficiency of common envelope evolution, which is this alpha parameter here. And you see that even within the measurement of gravitational waves that we know, the local rate of that we know, there is still a room for a lot of uncertainty, and especially the uncertainty towards higher redshifts. So this is one point of uncertainty. Another one is this time delay distribution that I mentioned. So these population synthesis models typically predict a distribution of 1/t. But like we see here in the left side, so you should look at the black curve. But there are some indications that maybe this is not the exact distribution. So this on the right, I show a result from Benjamin and Piran, who looked at the distribution of pulsars in the galaxy, and they measured the expected time distributions, and this is the black histogram. And you see that the red curve, which is supposed to be the distribution of 1/t, doesn't really fit the observed distribution. So we still don't really know the exact distribution of time delays. Now, another difficulty, as I mentioned, is the fact that if you produce these air process elements in dwarf galaxies, some of them may actually escape the galaxy altogether, and there have been some works on this as well. So here I want to go in slightly more detail. So imagine you have this this galaxy, and there was some event, either a binary star merger or a core collapse supernova, that produced the heavy elements, and this is the yellow circle. This event produced a blast wave that basically ejects the elements. And if the event is energetic enough and the galaxy is small enough, then of course these and if the event took place near, let's say, the outskirts of the galaxy, then all these elements will be ejected and nothing will be kept inside. So we looked into it a few years ago with Paz Benjamin and Joe Silk, where we look at the selection of dwarf galaxies. We assumed a certain density profile of these dwarf galaxies, and actually we looked at some general process that forms these heavy elements with some energy explosion. And we characterize the galaxy potential well by the velocity dispersion. And then we ask the question, how much of the heavy elements produced in the dwarf galaxy can actually be retained inside? And so here I show this plot show as a function of the characteristic length scale of the galaxy, or basically the radius on the x-axis and the velocity dispersion on the y-axis. The colors show the fraction of elements that would be retained in the galaxy. So here the different plots are for different explosion energies and also the mass of the gas at the time of explosion. So here you see that actually in our model, most of the time, a lot of the heavy elements are retained. So retainment function of say above 50%, especially for the numbers that we see in the galaxies that we looked at, and the reticulum 2 is here in pink. And here this is again a similar set of plots, but for a higher explosion energy. And if the explosion energy is higher, of course, then you retain less elements inside the galaxy, but you still retain a very significant fraction inside. So you do expect to actually what we showed here is that you still expect to retain a fraction inside these dwarf galaxies. And then what you can do from here is to look what constraints can you put on the rate of this unspecified event and the mass per event. So what we did again, based on this model in the previous slides, we took again a selection of dwarf galaxies and just drew the number of events that produce air process elements and the random times on which they were set off. For each galaxy, of course, we also estimate the number of stars that you had to form before the event took place, given the iron abundance, and we compared it with the observations of iron and europium in each galaxy. In fact, for all the galaxies except for reticulum 2, it was the only upper limit for europium. For reticulum 2, it was the actual measurement. And what we did from this is that we could constrain the mass per event here on the x-axis and the rate of these events relative to the supernova, the core collapse supernova rate. So this confirms what I told you before, is that these events have to be very, very rare. So this is below 1% of the core collapse supernova rate. So these are the confidence contours that I show you here. And then the mass per event is 10 to the minus 5 total in europium, and this is consistent with what we measured from this gravitational wave and kilonova event 1708-17. So there are two blocks here, but if we look at the red block, which takes into account all the elements above atomic number 69, then this is consistent with our very simple model. Now the two different plots here explore two different types of gas loss from the galaxy. because, well, this is an additional complication where so you form stars. The stars then some of them form supernovae, and they some of them then form neutron stars that merge or whatever, form upper process elements. But they also some gas is expelled out of the galaxies, and so this also influences this retainment fraction. So okay, so knowing that this explosion have to be rare, and we also have some constraint on the mass per event. Can we say something more about the exact process that formed them? So another process that we need to take into account, I'll come back to that a little bit later, is the turbulent mixing of these process elements in the interstellar medium. So this is from a paper of Benjamin and Otakizaka, where they proposed this sort of analytical approach or semi-analytical approach to explain turbulent mixing. Now I'll say a bit more of this about this in a few slides, but basically the idea is that if you form you have some event that formed the process elements at some point in the galaxy. It takes some time for the elements to diffuse in the ISM, and then depending on when and where the new stars were born, they inherited more or less of these process elements in their atmospheres. And so with this this model, they showed in this paper that they kind of couldn't explain the high metallicity end here. Although what I'm going to be interested in is more the low metallicity end. So we're going to use this same model, but in a bit different way. Okay, so now I'm going to present a more sort of complete model of the Milky Way line galaxy that we worked on in IAP. Now, this is still a semi-analytic model, so not a full numerical model, and there is a bunch of ways to improve it that I will discuss later. So this is a semi-analytic model. That means we build a sort of merger tree of dark matter halos analytically, and inside each of these dark matter halos, we plant the galaxy sort of by hand, and then we let them evolve along the branches. So the galaxies evolve along the branches, then they merge with different galaxies, and until we get to the present time, which is the Milky Way-like galaxy. And inside each dark matter halo, we have the CGM. We have the hot gas that cools, forms stars. So this is supposed to represent stars. And then the massive stars explode and form binary neutron stars. So this is supposed to be the binary neutron star. Stars also produce, of course, elements that they eject back into the ISM. And we have supernova heating and all that. And so we model in this way the evolution of the different phases of the gas inside the galaxy, the sterile populations, and the populations of the binary neutron stars. So we form the binary neutron stars from according to this model by Fryer et al. There is slight dependence on metallicity of the progenitor stars. And we have, but other than that, it's a very simplistic model where we just have an efficiency parameter for the formations of these binaries. And we have a certain yield, so our process elements form per merger event. This is, of course, the generative efficiency parameter, as I told you before. You have more events that have high smaller yields or vice versa, but this is not completely free parameter still, because we have some constraints on the yields and on the efficiency as well. And we tested a few models of the time delay distribution between formation and merger. So these are phenomenological models with some parameters as well. So this is either 1/t, log T over T, or some model from tabulated from this stellar evolution study. And what I want to mention is, of course, as you would expect, there is a huge there will be a huge dependence on the exact shape of this time delay distribution at small time delays. But in fact, unfortunately, stellar population models do not resolve, or at least do not publish the data for this very small time delays, because usually they're not interested in them. and they're completely crucial for this type of model that we see here. So you see here the different these ABC models where the minimal time delay is different, and they're tuned to produce the same mean time delay. But so what is going to matter is both the average time delay, but also the minimal time delay, or the time delay, or the number of events with, let's say, small time delays. Okay, and so this is what this model gives us. It's the I show you on the y-axis the log of the merger rate of binary interstar merger in the model. So the model is the dots, the colored dots. Each dot is the proto galaxy. So let me go back. So in this merger tree, in each dot I have a small galaxy or a proto galaxy, and so I can measure the merger rate inside this galaxy, and in each one corresponds to a dot on this plot, color coded the age of this of each proto galaxy, and this blue point is the final result, my sort of Milky Way like galaxy, as a function of the stellar mass again of each of the proto galaxies. And what I show here is that our model is sort of I will say qualitatively consistent with stellar evolution models that are shown here by these lines. Well, the blue and the orange lines. This is from Artala et al. Because in the paper they give the merger rate as a function of stellar mass, and it's sort of consistent, as well as the measurement of the galactic double neutron star. This is the estimate of the rate. So given this model, we can now calculate what is the abundance of europium in each of these galaxies, and the result I have is here. Maybe not completely satisfactory, and I'll see next how to improve it. So here again I show you in the same plane europium over iron on the y-axis and iron over hydrogen on the x-axis. Again, these measurements from the Milky Way in gray, and I show you the color plot, color points are the results of these three models with three different time delay distributions. So, well, first of all, it's not that bad because still at very low metallicities, we kind of reproduce some halos actually have relatively high abundances in europium, although not as high as some of the observed stars. And here I show you some of the model parameters. And now what actually the problem here is that this model inherently assumes instantaneous mixing of the of all the elements in each galaxy. So as soon as they're produced, they're immediately mixed inside this proto-galaxy. So of course this cannot actually reproduce the different inhomogeneities that exist in these proto-galaxies. And now this was difficult to reproduce with the semianalytic model, but we were inspired by this turbulent mixing scheme, and we implemented it in our model. And the idea here is that actually in reality, the binary star mergers occur at random locations inside the galaxy. Maybe not completely random, because you would expect at places where the stellar density is higher to have also higher density of BNS mergers, but still it can be sort of random, especially that these are very rare events. So the random component is important. And then these are process elements diffuse in interstellar matter. So according to this, this is the solution to a diffusion equation. So the density at any given point, at any given time of europium depends on the time since the closest event and the distance to this event. So let's imagine that we have some events that produced our process. These are the black points. So at time one, they just polluted a small region around them with our process elements. At time two, this region expanded a bit, but the density also decreased. That's the red circles. At still later time with the pink circles, the region polluted with our process elements is still greater, but then the density is also slightly less. Okay, but now let's imagine that we have these what we call observer stars, so stars that formed in the same galaxy, and then they inherited the abundances that we that are there in the interstellar medium. So if the star was formed like here, so very close both in time and in space to an R process event, then of course the abundance will be extremely high in its atmosphere. If the star was formed slightly later and slightly farther away, the abundance of R process that it inherited is smaller. And if it formed really far away, maybe it didn't inherit any R process elements or very few. And so by taking this into account in our model, we now obtain this result, which shows now the small dots are again the measurements. And this sort of histogram shows the abundances of these observer stars in our model, and the thick lines show the 5 and 95 percentiles in each metallicity bin. So taking into account this turbulent mixing, we're actually able to explain these observations even at low metallicities and even without having extremely short time delays. So of course now when we introduce a whole bunch of new prescriptions, and in particular we introduce this new parameter, which is the diffusion coefficient, which is given here. But then the results obviously depend not only now on the yield and the rate, but also on the diffusion coefficient. So the model now depends on this as well. Maybe it's a manner to actually measure this parameter. Now we can also look at we can also compare models with different models for this time delay distribution. Now here on these plots, I show only the 5 and 95 percentiles in each metallicity bin for different models. So on the left, I show the results where I took different models for the time delay distribution, but calibrated so as to have the same average delay time. And if you have the average delay time, so towards, let's say, the end of the evolution, towards reaching 0, let's say, they all converge towards the same thing, but there's some divergence at very low metallicity, so at early times. And on the right, I again have these 3 different models, but now I calibrated them so as to have the same fraction of very fast mergers, and the fast mergers I define as having merged within less than 100 mega years. And then they slightly diverge even at later times. And we see here that it's actually very important, the fraction of this very fast mergers. So what we saw here, it's just actually the beginning of this work, because there are still a lot of unknowns. And the model, again, it's a semi-analytical model where we implemented some known physics, but there is still a lot to explore. One question that actually arises is, why do we have this discrepancy with earlier works, especially the numerical models, like I showed before? So there are a lot of differences. First of all, our model is semi-analytic, so it's different to compare. But one major difference is that, another major difference is the binary star formation efficiency. So in this numerical model, in most numerical models, actually, they take a constant formation efficiency of neutron stars relative to the just total amount of stars you form. Whereas in our model, this number, this efficiency as a function of, let's say, metallicity, is varying. It's varying as a function of metallicity, as a function of stellar mass, and there is a huge dispersion. So as I showed you before, this just inside of each galaxy, and this is a result of the fact that we have this slightly more detailed model for the formation of neutron stars. There's a slight dependence on metallicity, and this is one difference. The time delay distributions in our model are different from the time delay distribution in this in previous numerical models as well. We have a different description of turbulent mixing, obviously. There are also some differences in our process yields, but there is a lot of work left to actually compare the models or gain some better understanding about the role of binary star mergers. So what are the next steps to do that? Now, there is actually a lot of work to be done. First of all, we still need a better model for the collapsar contribution. So this other candidate site for our process elements. For the moment, there are very, very few models. And the reason is, well, first of all, it was never directly observed. And In fact, each numerical model, you need a very sophisticated magnetic hydrodynamical model. There are just a handful of those. Each time you just explode maybe one star with particular mass, with particular metallicity, and the results are sometimes inconclusive. So it's different to draw some particular conclusions and to implement them in a Milky Way, like in the Milky Way evolution model. So the better model is needed. Then, of course, we need better rate estimates for the BNS mergers. Obviously, if we want to explore the abundances at the low metallicity end, it's critical to understand what were the merger rates of binary stars at early epochs. So this is still poorly known. Is there a population of these fast merging binary stars? One clue that we can have is one additional tool is to use also radioactive R-process elements, because the radioactive R-process elements give us another time scale in the problem. So here in this paper, they actually proposed to do that. So here they looked at the abundance of R-process elements in the early solar system. So this is from meteorites and the deep sea measurements. So at the, let's say, present epochs, and with this dashed lines, never mind. But basically the solid lines are models that they try to fit to both these measurements, knowing that the half-life here was 80 mega years. So this is just another clue that can be used to break the degeneracy that I told you before between the rate of the events and the mass per event. Of course, we expect to have a better constraints on the binary star merger rate from the next gravitational wave data. This plot on the left shows the horizon for current and ongoing gravitational wave experiments. So LIGO, Virgo, Kagra, that are operational and will start hopefully at let's say sometime next year. This plot shows the horizon for observing binary stars. It is expected to greatly increase, and so the rate of detection will increase as well, especially, and also LIGO India will join. And the plot on the right shows the redshift range of the horizon, again, for binary for all types of systems with future detectors. So the green is for Einstein telescope, and the rose is for Cosmic Explorer. And so for the binary stars, where somewhere here, we'll see up to redshift of 2, so up to the peak of the star formation. That will give a huge amount of measurement and really help constrain the rates. Of course, we also hope to have many more electromagnetic counterparts to these observations, which will help us also constrain this process of kilonova itself, maybe the mass ejected per event, and this ejection process itself. So for the moment, only one event has been observed, both in gravitational waves and in electromagnetically. There were another binary star merger detected in gravitational waves, but not electromagnetically. The reason is that, first of all, they're very poorly localized usually, and also if they're far away, they're too faint. And in this Astro 2020 white paper, here they basically discuss the fact that with future instrument like KLT, we'll be able to observe this kilonova. Here is what is shown is the kilonova light curve, even to much higher redshift. So this is the black is the 1708-17 event that was observed, but hopefully in the future we'll be able to observe events much farther away, and so constrain much better this process, and hopefully determine where do these elements come from and where is cold produced. And thank you for your attention.
Thank you very much, Irina. So now we are moving to the breakout rooms.
Can you say bye to the people on YouTube?
Yes, I'm sorry. So the people on YouTube, thank you, Marina. For the people listen to us on YouTube, we are going to stop streaming. And next week, we are not having our weekly seminar because it's the Semana Académica at URGIS. So we see in the first week of October. Bye.